here's what I would point out. So essentially the idea here, here's how I like to think of it. Who knows what an ant farm is? I know it's a weird. So a few of you. So an ant farm was I had one as a kid. It's like this little like rectangular thing, and you put like little white like rocks, kind of sand-ish stuff in it, and then you put ants in it, and they like make little tunnels and stuff and everything. And the sand kind of is like not all level, right? But the amount of sand, rock, whatever, never changes in this little rectangle thing. So if without ants in it, you were to shake it up and all of it was leveled out, that height would be the average value of whatever the function was that was representing like the actual height. So it's kind of like the average height of the sand. If you leveled it all out, it would all be at that one height with the same amount of area. That's the whole idea. Is you're just trying to find what would the average height be if all of your area was a rectangle all at the same height over the same base. It's really easy to calculate. Here's how we calculate it. So for f of x on some interval from a to b, the average value of f of x is given by the integral from a to b of f of x, aka the area under the curve, divided by the width, divided by b minus a, or more nicely written as 1 over b minus a times the integral from a to b. So if you now define a definite integral, finding the average value of that definite integral is super duper easy. You just divide by however long the interval was. Not too bad. So for example, we could find, say, the average value of f of x equal to 3x squared on the interval from 1 to 3. Cool. So here's how we're going to do it. It's going to be equal to 1 divided by 3 minus 1 times the integral from 1 to 3 of 3x squared dx. This is a pretty easy example in that, right? We can set this equal to, well, let's see, not set equal, we can find it. So that's going to be 1/2 times, let's see, the integral of 3x squared is x cubed, evaluated from 1 to 3. So we're going to get 1/2 times, that's a 3 in case you can't tell, 3 cubed minus 1 cubed, which is going to be 1/2 times 27 minus 1. And 1/2 of 26 is 13. So on that interval, in fact, I'm going to show you a picture. On that interval, the average height of the function is 13. So let me show you what we mean by this. It's much nicer if I just do this here. So we've got our function y equal to 3x squared. And let's go ahead and limit ourselves to the interval from 1 to 3. That's not very great. So let's do this. So there's my, oh, that's kind of big. Let's zoom out a little bit. Okay, so there's my function. And to make it look even nicer, you can do the following. You can do this. If you want to actually look at the area, you say y is bigger than or equal to 0 and less than or equal to the function. So there's all the area. And what we're saying is on that interval, and I'd like to make this look a little nicer, but fine. On that interval, we're saying that this y equal to 13 is the average height. So that blue line, if we find the area under it, those two areas are the same. The area under the red curve and the area under the blue curve. So that height right there, saying this red function over this interval has that average height. Or in other words, if you imagine this was like an ant farm with a very steep incline and you shook all the sand, it would come out to be level at a height of 13. Area hasn't changed. We've just redistributed how it is looking as a nice rectangle as opposed to some steep curve. And there's really not a lot else to say about average value. You find the definite integral and you divide by the length of the interval. Now, what I will say, this is for next quarter, when you find the average value, instead of a line or a curve over some interval, it's going to be the average value of some surface over some region that's two-dimensional. But the idea is still going to be the same. You're going to take the volume under this and say, well, if I shook it all out and made it flat, what would the average height be? Instead of being area divided by length, it's going to be volume divided by area, but you're still going to end up with an average height. So that's for the future. Just want to point, because it's a little harder with 3 dimensions and the calculations are not quite as easy, but it's still the same idea. What am I looking at over here? That's not what I want to look at. So let's see. But how more? Oh, and then one thing we could ask is, no, Dave, want to ask that? Not really. No, I don't. There's nothing. I find average value not particularly interesting. So, but let's actually move. We'll talk about one more example, because sometimes the questions are not so straightforward, like the next one. So here we go. Yeah. In some city, I don't know which city, some city, the temperature in degrees Fahrenheit, T hours after 9 a.m. is modeled by this function. The temperature at time T is equal to 50 degrees Fahrenheit plus 14 times sine of pi times T over 12. We want to find the average temperature between 9 a.m. and I'm going to pick a more interesting, let's see, 9 a.m. and sure, 9 a.m. and noon. Okay. Still a relatively straightforward calculation. We're just going to, again, find the integral of this function over the interval and then divide by the length of the interval. So here, we should be getting that, interesting. Yeah, no, that seems all right. We'll have to think about this, yeah. Okay, so the average value here, we have to be a little bit careful about our limits of integration. Because you might think, well, if I'm going from 9 to noon, they should be from 9 to 12. But they're not, because of the words in the question. So we read the words very carefully. The words say, in some city, the temperature T hours after 9 a.m. is modeled by this function here. So when T equals 0, that's actually the temperature at 9 a.m. So T of 0 is going to be 50 plus something, and that's going to be the 9 a.m. temperature. And then at noon, we've had how many hours elapse? 3. So we're not going to be integrating from 9 to 12. We're going to be integrating from 0 to 3 because of the words that were written. So it's going to be the integral from 0 to 3 of this function, 50 plus 14 sine of pi over 12 times t dt. And then we're going to multiply that by 1/3, or 1 over 3 minus 0. Right? That's the total, like, temperature. Like, it's weird to think about total temperature. Like, you added up all the temperatures. That's kind of a weird thing to say. But when we divide by this number, we're going to get the average temperature. All right, the rest of this is just kind of gross calculation here. I knew I didn't want 3. I really wanted. I want to make the numbers come out a little bit nicer. It's just slightly. So I'm going to change that to, I don't know what I'm going to change it to. 11 a.m. is what I really want. Sorry. I know it's terrible. But I like nice numbers. So we'll change that 3 to a 2. Apologies. There we go. Much, much better. So now, no, it's still going to be terrible. Oh, well, we'll live with it. Sometimes you just have to get gross numbers. Try to make things nice, and what happens. So let's see, we're going to integrate this. We're going to get 50t plus 14 times the antiderivative of sine of a multiple of t is going to be negative cosine of pi over 12 times t divided by pi over 12. Evaluated from 0 to 2. Right, just like when we evaluate, like, or integrate, I should say, sine of 3t, we get negative cosine of 3t divided by 3. Same idea. We're just dividing by the multiple of t here. And then plugging this in is terrible. We get 1/2 times, let's see, plug in 2, we get 100. I'm going to write this as minus, so let's actually do a little bit of simplifying here. 14 divided by pi over 12 is going to be 14 times 12 over pi. And then we're going to have cosine of 2 times pi over 12. Minus, now we're going to plug in 0. So we plug in 0, 50 times 0 is 0. We're still going to have minus 14 times 12 over pi. And then cosine of 0 is 1. Wow, that looks terrible. Who thought of this nice question? That was me. So let's see, we have 1/2 times numbers that are awful. 100. And this is gross over here. Ugh. I would probably just leave it like that. Okay, not really. I probably wouldn't really, but I would be very much like, good God. So let's see, 14 times 12 is 168 over pi. And then cosine of pi, I was trying to make this number come out nicely. I blew it. Cosine of pi over 6 is the square root of 3 over 2. And then we have minus a minus, so plus also 168 over pi. And I would definitely stop there. That seems awful enough. There's your average value, whatever it happens to be. I don't know what that is. It's a number. Is it bigger than 50? Maybe. Smaller than 50? Maybe. It's a lot bigger than 50 though, because I think on this interval, the sign of these numbers is positive. But again, not really the point. The point is you're just kind of throwing this thing into this formula and doing the calculation. It's just the integral divided by the length of the interval. So average value shouldn't be scary at all. It should be like, oh yeah, easy. I'm just gonna do the integral and then divide by however far it is from A to B. In this case, from 0 to 2, we divide by 2. Yeah. All right. Should we do one more? One more with less terrible numbers, maybe? He's like, no. Okay. We don't have to do another one. If we feel like it later on, we can do a fish one. Fish. All right. Let's talk about some other biology applications. Further applications to biology. Oh, I should pass around the attendance sheet before I forget. Here we go. So there's a few kind of weird formulas that you might end up memorizing if you do them long enough, but usually most people don't want you to memorize them. The first one we talk about typically is survival and renewal. And renewal. So here's the setup. And I'm going to kind of write out all the things here. Suppose we start with an initial population, which we're going to denote as P sub 0, also known as P naught. New members of whatever, like we keep talking about birds or cells or whatever kind of thing we're talking about. New members are added at a rate R of t. R of t could be a function of time. It could be a constant, which I guess technically is still a function of time, just not one that's changing. So you're going to have some function of time. That's how we're going to add new members. And then, and the percent of the population that survives t years from now, or from time equals 0, is given by the survival function, which we denote as S of t. I should also point out the little t's are time. Well, the little t's are time as a variable. There's going to be a big T, which is going to be time as like a value, which feels weird, but it's fine. Okay, so just again to point out here, what we have going on is R of t equals the renewal function, right? It's how we're getting more members of our population. And S of t is the survival function. It's the number of members that live to the next year, essentially, or to whatever year we're talking about. So here's our formula for the population at time t. I should say the population t years into the future. I need to double check one thing because I feel like I've made a slight error. I just want to double check. Yeah, that should be a cap. Yeah, okay. Population capital T years into the future. Sorry. Is given by the following. P of capital T is going to equal P naught multiplied by S of capital T. So that's not the whole thing, but I'm going to pause a second. So P naught is your initial population, and S of capital T is going to be the percentage of that population that lives for capital T years. So if you take your initial population and multiply by the percentage that are going to live that long, you're going to get how many have survived that long. Plus the integral, oh, sorry, what'd you get here? Yeah. The integral from 0 to capital T, this is the part that's kind of weird, S of capital T minus little t times R of little t dt. Essentially, this part here is calculating at the same time the number of new members you're adding along with the fraction of them that survive long enough to get counted. Which I know feels like a lot to say right there, but that's what's happening there. Most people don't require you to memorize this formula, but you should definitely ask your instructor if you have to memorize it. I think they usually give it to you if they're going to make you use it on the exam. I usually remember when I first taught this class for a few years, I was like, I have no idea what this formula is. At this point, I've taught it enough times that I usually remember it pretty well, usually. Most of our job when doing this is identifying what pieces go where and then doing the integration. So let's look at some examples. Make sure I've got the right things written down here. Yep. So, let me actually write one more thing down here, just for example. So this is right, this part right here is like the surviving from the new members from t equals 0 to t equals capital T. So for example, if t is equal to 1, R of 1 is equal to the new members you have after 1 year, and capital S of t minus 1 is the percent that survive the t minus 1 years they're going to be alive. So essentially, yeah, you're finding the number of new members you have at that time, and then you're multiplying that by the percentage of them that survive the remaining number of years they have to survive to make it to the time we're actually interested in. All that to say, you don't really need to remember any of that. You need to know how to throw things into the formula and calculate the things, but actually knowing what all of it means super precisely, probably not super necessary. So let's look at an example. A population. These examples have so many words. Of insects currently numbers 22,500 and is increasing at a rate of R of t equal to 1,225 times e to the 0.14 t insects per week. So notably here, as time increases, this rate is going to increase, right? That R of t is going to be larger the longer time goes on because there's going to be more insects and they're going to make more insects. The survival function for insects is S of t equal to e to the negative 0.2 t. Again, where t is measured in weeks. So as time goes on, this number gets smaller and smaller and smaller. So the percentage of insects that survive gets smaller the longer time goes on because, right, insects don't live that long. So the question is, how many insects will there be after 12 weeks? And all we're really going to do is we're going to look at this formula here, and we're going to identify all the pieces. So some of them are already told to us explicitly. P naught, that's your initial population, is going to be 22,500. Your R of t is what they already told us. It's 1225 e to the 0.14 t. S of capital, what's capital T here? Our capital T is how much time we're interested in, which is 12 weeks. Our S of capital T is going to be S of 12. So we're just going to take our S of t and plug in 12. So we're going to get e to the negative 0.2 times 12. And then in my opinion, the weirdest part, the S of capital T minus little t is going to be S of 12 minus little t, which is going to be e to the negative 0.2 times 12 minus little t. Oops, sorry, I can't see all that. Apologies. And then we're going to toss all of that in to that formula. So we're going to say that P of 12 is equal to P naught, 22,500, times S of capital T, which is S of 12, which is this part here. Let's simplify that as e to the negative, let's see, 0.2 times 12 is 2.4, plus the integral from 0 to 12 of this part here. Again, let's simplify that as e to the negative 2.4 plus 0.2 times t multiplied by my r of t, which is 1,225 e to the 0.14 t dt. Kind of a lot, but not unmanageable. Here's what's typically going to happen at this stage. You're going to simplify as much as possible. I'm going to leave this alone, or maybe write that as 22,500 divided by e to the positive 2.4. I don't really care which way I write it. But this integral we're going to deal with. So dealing with that integral, we're going to pull out any constants. I'm going to point out that this part right here, this e to the negative 2.4 times e to the negative 2.4 plus 0.2 times t, we should really break this up as e to the negative 2.4 times e to the 0.2 times t. So that we can combine this e to a thing plus times this e to a thing. So, and I should have left myself a little bit more room here. Let's use a new piece of paper. Let's go ahead and write this down here. And say that that's going to end up being P of 12 equal to 22,500 times e to the negative 2.4. And this, we're going to pull out the constant of 1225. We're also going to pull out the e to the negative 2.4. And we're left with the integral from 0 to 12 of e to the 0.2 t times e to the 0.14 t, which we really should have combined as e to the 0.34 t. Then we're going to simplify. So we're going to do this integral now. So we're still going to have 22,500. Let me look at one thing here. I'm curious about. Over e to the 2.4 plus 1225 over e to the 2.4. And then we're going to integrate this. The integral of e to a multiple of t is going to be e to that multiple of t divided by that multiple of t, evaluated from 0 to 12. So we're going to get 22,500 over e to the 2.4 plus 1225 over e to the 2.4 multiplied by e to the 0.34 times 12 divided by 0.34 minus e to the 0 is 1 over 0.34. And then you can plug that all into a calculator, which seems really gross, and get approximately 19,005. Interestingly, I think at least, the population has decreased, right? We started off with 22,500 insects, and we've lost a couple thousand, like 3,000-ish, 3,500-ish. So typically for these problems, you do need to use a calculator or some sort of calculation device to actually get an idea of what the value is. Because, right, leaving it like this, although this is totally correct, I don't have a very good idea of what that number is until I've actually used a calculator to actually get closer to the approximate value. Oh, except I made a mistake. Sorry. It's not a huge mistake. This part is the 19,005. This part's approximately 2041. Sorry about that. So we're actually getting approximately 2041 plus 19,005, which is still a decrease, but less of a decrease, which is going to be approximately 21,046. Okay, we didn't lose as many insects as I thought. Yeah. Yes, question. Right. So the capital T is actually the amount of time that we're being told has elapsed during this process. So the fact here that we were told that we want to know how many insects there are 12 weeks from time zero, that's your capital T. So T, capital T is your end time, whereas lowercase t is your variable that's going to show up in your interval. So, and again, let's look back at the formula for a second. Right. So here in this, so sorry, in the initial formula way over here, apologies. So looking here, right, you're getting your initial population, whatever that is. I don't know how I did that. Okay. It's just a day for technology not to work for anybody, apparently. Let's see, where'd you go? Oh, there we go. Okay, cool. Great. So, right, this S of T here, this is your survival rate after T years or weeks or whatever the unit time. So you're actually plugging in the value of 12 there. And then over here, you're doing the interval from 0 to 12. S of 12 minus what, leaving T just as is, and then R of T if there's a T there, right? So you're plugging in actual numbers for each capital T and then leaving the lowercase t's as they are. Yeah, it'd be nicer if we could use different letters, but that's not how it's written. Let's see. I feel like I should do another one of those, because those are kind of, yeah, let's look at this one over here. Sure. So let's look at one more survival and renewal. Yeah, we should start with a new piece of paper. And it can really be used for lots of different contexts. That feels like very unfocused. Okay. So let's look at another example. The drug is administered intravenously, to a patient. It's all the way over here. Look over here. At a rate of 10 milligrams per hour. The patient's body. So you can write down all these words, but you might just try writing down like the things we're going to try to interpret as what's what. The patient's body eliminates the drug over time so that the proportion that remains in the body is e to the negative 0.25 times t. If the patient currently has 70 milligrams of drug in the body, in their bloodstream, I should say. How much drug will be present 8 hours from now? So again, our job mostly is to identify what piece is what piece and then throw it all into that formula. So to me, it looks like our initial population, in this case, our population is the number of milligrams of drug. Our initial amount is 70 milligrams. The amount of time that's going to pass, our capital T, is 8 hours. Our renewal rate is 10 milligrams per hour, right? We're giving the patient, renewing the amount of drug in the body, we're adding the amount of drug in the body at 10 milligrams every hour. So our R of T is 10 milligrams per hour, but I just care about the number really. Notice in this case, R of T is constant. That's fairly typical. And then our S of T, our survival rate, is e to the negative 0.25 times T. Right? They tell us with lots of words, the patient's body eliminates the drug over the time so that the proportion that remains, oh, those are keywords that tell us that's the survival rate. The amount that's remaining, the proportion that's remaining is this function. So that's our S of T. And then you don't have to, but I do like to write down the S of capital T minus little t is going to be S of 8 minus little t, which is going to be e to the negative 0.25 times 8 minus t. To me, it just helps to write that down. So then all of that is going to tell me that P of capital T, which is 8, is going to equal my S of 8 times P naught plus the integral from 0 to 8 of my S of 8 minus T times my R of T dt. Then we just start plugging everything in. So S of 8 is going to be e to the, let's be smart about this, 0.25 times 8, 1/4 times 8 is 2. So that's going to be e to the negative 2. My P naught is a 70 plus the integral from 0 to 8 of this thing here. Let's multiply that as well. Negative 0.25 times 8 is negative 2. And negative 0.25 times negative t is positive 0.25t. So I'm going to get e to the negative 2 plus 0.25t. And then my R of t is just 10. Here's how I should simplify this. This is going to equal 70 over e squared. Plus, I'm going to pull out the 10. I'm also going to pull out the e to the negative 2. I'm left with the integral from 0 to 8 of e to the 0.25 times t. Never enough room on a single piece of paper. So let's see. Going further, we're going to get 70 over e squared plus 10 over e squared. Integrating this, we're going to get e to the 0.25t divided by 0.25, evaluated from 0 to 8. We plug it in, we get 70 over e squared plus 10 over e squared. Plugging in 8 e to the 0.25 times 8 is still e squared. Dividing by a fourth is like multiplying by 4. So we get 4e squared minus, if I plug in 0, I get e to the 0 over 1/4 or just 4. That's really e squared over 0.25. That's really e to the 0 over 0.25. And then, yeah. So simplifying this slightly more, I've got 70 over e squared, 10 over e squared times 4e squared. The e squareds cancel and you get 40. And then 10 over e squared minus 4 times negative 4 is minus 40 over e. So we can simplify this pretty nicely to 30 over e squared plus 40. And then if you actually wanted to know what that was, I would need a calculator. using a calculator. I guess I could use my computer. It's literally right in front of me, but my phone's right there. Let's see. 30 divided by e squared is going to be. You should never use your phone calculator. It's the worst. As I do it right in front of you. 30 divided by e squared. Wow. See, I can't even use my phone calculator. Doesn't even work. Let's see. E squared. Can I do e squared? Probably not. There we go. And then 30 divided by that. Sure, it's about 4-ish. That's a gross approximation. See, I can't even use my calculator, right? All right. So the thing to know about the survival renewal function is just knowing where to plug things in the right place. Occasionally people ask weird questions. There's one kind of question that usually gets asked, which we'll talk about maybe next time if we want to, where like you have to figure out what the renewal rate should be if you want the amount of drug in the body to remain constant. But I think we should wait on that one for a number of reasons. Mostly because we have other things to talk about in the last 11 minutes we have here. So we'll probably start talking about volume next time. But let's go ahead and do a couple more things here. There are a couple other interesting applications. So another one is cardiac output. And the idea here is it's the volume of blood pumped by the heart per some unit of time. And there's kind of a lot to say here. So I don't really want to highlight this. So to measure it, what we do, at least what people say we do, to measure it, we inject dye. Dye is injected. You probably don't need to write down all these words. Into the right atrium and flows to the heart. That's much better. Okay. Flows to the heart into the aorta. That might be too high, actually. And then a probe is inserted into the aorta and measures the concentration, not the amount, the concentration of dye leaving the heart at equally spaced intervals. Okay, we're almost there. I know it's a lot of words. Until the dye has cleared. Okay, so that's the process. Here's how we calculate things. So here's what we're going to say. We're going to let C of t equal the concentration of the dye at time t. And it's going to change, right? Because the dye is leaving the body, probably decreasing. F is going to equal the flow rate of the blood. And A is going to equal the amount of dye. So here's the calculation that makes sense to me. The amount of dye is going to equal essentially the concentration multiplied by the flow. So the concentration at this time multiplied by the flow for that time interval, plus the concentration at another time multiplied by its flow, and so on and so on and so on. So we're going to say that the amount of dye is going to equal the concentration at time 1 times the flow rate times the amount of time elapsed, plus, and then it's going to be the concentration at the next time interval times the same flow rate, okay, because your blood flow rate, we'll assume is pretty constant, times the same time interval, and so on and so on. We just keep doing this. The next concentration times the flow rate times delta T, and so on and so on until we're done. Or, in other words, this might look pretty familiar, right? When we add a bunch of things like this, that's leading us in the direction of an integral. So this is going to say that the amount of dye is equal to the integral from time equals 0 to, again, however much time we're using, capital T, and then we're going to have C of T, the concentration at whatever time, times F, the flow rate, and the delta T becomes the dt integral. The flow rate's a constant, the amount of dye is a constant. We're typically interested in solving for the flow rate, so we're going to factor that flow rate constant out, and then we usually solve for F. So we're going to say that capital F is equal to the amount of dye divided by the integral from 0 to T of the concentration at time T. That's how we typically calculate cardiac output. I've never, ever remembered this formula a day in my life. You probably don't need to memorize it either, but it's good to see it. What kind of question could we ask? Well, one where we're kind of given all the information up front. So here's an example. That's interesting. Where'd you come from? I feel like this is one of those days I was trying to write the same problem a million times. So for example, we could say the following. This method, the dye dilution method, which I guess is what this is called. Right, don't ask me about the biology. I know nothing about the biology, except for what the book tells me. The dye dilution method is used to measure cardiac output with 6 milligrams of dye. The dye concentration in milligrams per liter is modeled by the function C of T equal to 20 T e to the negative 0.6 T for time between 0 and 10 seconds. And we want to know what the cardiac output is. So find the cardiac output. Well, it's really easy to set up. There's the formula. The cardiac output is going to be A, which is my 6 milligrams of dye, divided by the integral from 0 seconds to 10 seconds of my C of T function, 20 T e to the negative 0.6 T dt. And the setup is really, really easy. And the integration is kind of a huge pain. Huge is probably enough statement. The integration is somewhat of a pain, right? Because this integral of 20 T e to the negative 0.6 T is an integration by parts problem. So what I would probably do is I'd probably do this denominator part off to the side. I would say, all right, well, the integral of 20 T e to the negative 0.6 T dt, integration by parts. So we're going to let u equal 20 T, du, let me see one thing here. Yeah, cool. I'm not doing too much. Our dv, apologies, is e to the negative 0.6 T dt. The du part's going to be 20 times dt. And the v part is going to be the antiderivative of this, which is e to the negative 0.6 T divided by negative 0.6. So when we do this integral here, our integral is going to end up equaling u times v. So 20t times e to the negative 0.6 T divided by negative 0.6 minus the integral of v du, which is e to the negative 0.6 T divided by negative 0.6 times 20 dt. And then we integrate that part. So let's see, we're going to have, yeah, this is gross. 20t times e to the negative 0.6 T divided by negative 0.6 And then we're going to have plus 20 divided by 0.6, right? Because it's a minus. And then when you integrate e to the negative 0.6, you're going to get e to the negative 0.6 t divided by negative 0.6 again. And then you get to plug in 10 and 0, and then all that is the denominator part. So our blood flow, our cardiac output here is going to be some gross fraction. It's going to be 6 on top divided by all of that with first 10 plugged in and then 0 plugged in. So it's going to be, all right, plugging in 10, I'm going to get 200 times e to the negative 6 divided by negative 0.6, bless you, plus 20 over 0.6 times e to the negative 6 divided by negative 0.6, minus, then we plug in 0 and we get 0 times whatever plus 20 over this times e to the 0 over that. So we're going to get 20 over 0.6 times 1 over negative 0.6. Yes. Sometimes these numbers are just so unfortunate. And actually, I should say, these numbers are not that unfortunate. It's really just that the setup is what it is. That the problem can't be really made much nicer. If we calculate this, we get approximately 6 divided by 54.58. That's what this bottom part's about equal to. And that's going to be approximately 0.11. What are our units? Let's see. The dye concentration was milligrams per liter, and this 6 up here was 6 milligrams. What should it be? I have no idea. I really have no idea. Let's see. So we've got what time is it? I have not much time. We have milligrams here. We have milligrams per liter here, but then when you integrate, you multiply by time. The milligrams end up canceling. You end up getting liters per time. And our time was second. So we get liters per second. Which makes sense, right? If you're talking about blood flow, it should be some volume per unit of time. So it is not a bad idea to check that the units make some amount of sense after that. All right, next time we'll start talking about volume.